Hello everyone, this is Mustafa here solving soil mechanics problems for civil engineering students, and in this video I'm talking consolidation. So we have a problem here, consolidation test done on a clay sample. We are given the vertical stress sigma dash Z and we are given the corresponding vertical strain. So row 1 for the vertical stress and row 2 is for the vertical strain. We are also given the initial void ratio being 1.21 here required. First is to plot the data on arithmetic scale, and then the same data to be plotted on a semi-logarithmic scale, and then we use the data to determine the pre-consolidation pressure sigma dash C using Casagrande method, and then finally we determine the compression index C sub C and also the swelling index C sub S. Let us see solution strategy for a problem of that nature. First, we need to convert the vertical strain to void ratio, and we need to draw then E versus sigma dash Z data in terms of the arithmetic scale and the logarithmic scale. Third is to process the data to determine the pre-consolidation pressure, and finally process the curves to get the compression index C sub C and C sub S. To solve a problem of that nature, we need to have essential knowledge. First, the definition of strain, and this would invoke this schematic here as the sample compressed by delta H. So we would have vertical strain epsilon Z equals delta H over H. The second is this phase diagram here to the right, which can link the change in height to the change in the void ratio. So as we have here a compression, say, of delta H, the void ratio will change by delta E, and we will have this important relationship. Delta H over H equals delta E over 1 plus E. Remember this one here, and this applies for any H. Now we can proceed. We convert the vertical strain to void ratio. We invoke this from the previous page, and then we can basically just substitute and rearrange this equation here. When we rearrange it, we will have the change in void ratio as a function of epsilon Z. We add E naught to both sides of equation 1, so that we have basically E naught plus delta E, and this left side here is the void ratio. Void ratio is the initial void ratio plus the change in the void ratio, and this will actually give us this important equation 2. That is the void ratio as a function of the initial void ratio and the change or the axial strain, vertical strain epsilon Z here. Then we can use the data given from the vertical strain, substitute it in equation 2 to get basically E. But there is something important here we need to note. That is, as the vertical strain increases, the void ratio decreases. As such, epsilon Z should be negative when we substitute in equation 2. That's very critical. Now let us try to get two values for the table above, and then we continue. So we bring here this equation 2 for epsilon Z equals 0.032. That's the first value. Substitute in equation 2. You can see here that the vertical strain is input negative here, and we have the corresponding void ratio 1.139. We repeat it for the second value of 0.041, and also it has to be substituted negative here, and this will give us the second value 1.119. Then we continue with the rest of the table, and this is a vertical strain here, not epsilon Z. Now we have completed the table. We are in a position to draw the data. So this is a arithmetic scale void ratio versus vertical stress, and you can see the void ratio drop in that direction or increases in that direction, and the vertical stress increases in the direction. Next is just to change this horizontal axis scale from linear scale to logarithmic scale, and this will give us this nice E log P curve. This should be very familiar. We have the compression side and we have the unloading side, because the last value here is 16. After we finished 1024 kPa, we unloaded the sample to 16 kPa, which correspond here to that value. Now we use the E log P curve to get the pre-consolidation pressure and also the compression index and the swelling index. Here, first, we pick the point of maximum curvature. So this circle here is basically an imaginary one. So basically you try to imagine that the smallest circle that can pass through this point. And from here we can move forward. First, we plot a horizontal line that's based on Casagrande method. And then we draw a tangent to the curve at this point of maximum curvature. Third, we bisect this angle that's between line 1 and line 2. So this will give us this green line here, 3. 4, we extend this linear part of the compression curve, which we call it the virgin compression curve. 4 and the 3 and 4 will intersect at this point here, X, this blue point, that's 5. From this, we go down 6. This will give us this point here. We'll continue. Next. So we have here basically this point A. We are now in a position to determine the pre-consolidation pressure. So this black dot here, or point A, represent the pre-consolidation pressure. Very important that we process this curve and get the right values from the logarithmic scale. Okay, some people may be a bit intimidated by the logarithmic scale, so we will have a chance here to process this relatively in detail. First, from this one here, which is a logarithmic scale, so this represents 0, log 1 is 0. So first, we measure this value here, because this is supposed to be on a piece of paper. So you can measure from, say, 1 to 10. That's exactly the same from 10 to 100 or 100 to 1000. So this came here, for example, as 32 millimeter. We measure exactly the same process from this point here, from point O to point A, which represent the pre-consolidation pressure sigma dash C. So this is 62 millimeter. Now we can use this to work out the pre-consolidation pressure. So basically from log 1 to log 10, it's 32 millimeter. We know that the difference in the log can be a ratio. So this is log 10 to 1, or log 10 is 32 millimeter. Exactly the same process we repeated. Log sigma dash C, which you are after at point A, because we are measuring from 1, so this is 62 millimeter. We can rearrange this here. Log 10 correspond to 32, log sigma dash C correspond to 62, so we can actually do this exchange, and this will give us the pre-consolidation pressure, sigma dash here, pre-consolidation pressure log, when we do this, is 1.968. This means that the pre-consolidation pressure itself is 10 raised to the power 1.968, which we got, that's 93 kPa. And this represents the pre-consolidation pressure we are after. So it's very important here to know how to process this, which is straightforward. The next step is to determine the pre-consolidation pressure, sigma C, which is the slope of this line here. And also for C, S is the slope of that line here. So we need to be smart in processing this. First, to get this slope is basically delta E over delta log sigma dash Z, because that's the vertical, the slope here is the vertical divided by the horizontal, which is correspond like to 10, this angle here. So we take this triangle outside, but we need to be smart. So you see the first point I picked here, that corresponded to a value that I know of the void ratio, 0.9. Also this one here is 0.7. This way I'll be just required to get what this base of the triangle represent in terms of the log. So I take this one outside, 0.9, 0.7, so delta E is 0.2, so delta E here is given. So I just need to measure this by the ruler, so it's 13 millimeter. I need to get the delta log of that. I have already got the 1 log unit corresponded to 32, which is this value here. So basically 13 millimeter divided by 32 millimeter give me the delta log along this base here, so that's 0.436. All I need to do is to plug it here. So based on this, C sub C is delta E, it's 0.9 minus 0.7, that's 0.2. Delta log is what this base is equivalent. We calculated this as 0.436, and this has given me 0.458. So the compression index delta E over delta log sigma dash Z is 0.458. We repeat the same for the swelling index, but also we draw this triangle so that we have a known value of the change in the void ratio, 0.7, 0.6, and this will give me delta E equals 0.1, as you can see here. And at the base of the triangle, I measure it, so 35 millimeter. So delta log is 35 millimeter, which is this base, divided by 32 millimeter, which is what the log unit would be equivalent in terms of millimeter. 32 millimeter, that's 1.097. I am ready now to substitute here in this equation. CS is also delta E over delta log sigma dash Z, but along the unloading curve. So I substitute here, that's 0.091. So this way we calculated the compression index and also the swelling index. There are lots of lessons learned from this. You need to know the meaning of the vertical strain or any strain in general. We need to know how to link the change in the height to the change in the void ratio or the phase diagram. Something need to be known by heart. And also we need to know how to process the data to get the compression index and the swelling index, as well as the pre-consolidation pressure. So hope to see you in more videos on the soil mechanics, consolidation, etc.